Now we are going to see about nanomaterials. We all know a meter is the distance from the tip of your nose to the end of your hand. 1 meter equal to 3.28 feet and millimeter is 1,000th of a meter and micron is a millionth of meter or 1,000th of millimeter. A nanometer is 1,000th of a macron. So it is represented by 10 power minus 9 meter or it is a billionth of a meter. We will see some of the nano definitions. A nano cluster. It is the collection of units of up to about 50 units. Colloids. It is a stable liquid phase containing particles in the 1 to 100,000 nanometer range. A colloid particle is one such 1 to 1000 nanometer particle. Nanoparticles. A solid particle in the 1 to 100 nanometer range that could be non-crystalline, an aggregate of crystallites or a single crystallite. A nanocrystal, it is a solid particle that is a single crystal in the size dependence of properties. Nanoparticles has a unique property, that is they depend upon all the properties depend upon their size. Composites made from particles of nano-size ceramics or metal smaller than 100 nanometers can suddenly become much stronger than predicted by existing materials science models. For example, metals with a so-grained size of around 10 nanometers are as much as 7 times harder and tougher than their ordinary counterparts with grain sizes in the micrometer range. The nanoparticles affects many properties such as melting point, boiling point, band gap, optical properties, electrical properties, magnetic properties. Even the structure of materials also changes with respect. The properties of materials can be different at the nanoscale because of two major reasons. That is, one is nanomaterials have relatively larger surface area when compared to the same mass of materials produced in a larger form. Nanoparticles can make materials more chemically reactive after the and affect their strength or electrical properties. Second reason is quantum effects can begin to dominate the behavior of matter at the nanoscale. Nanomaterials can be divided on the basis of three categories. One is that is zero dimension. That means length, breadth and heights are confined at a single point. Example for this one is nanodarts. One dimension. It has only one parameter, either length or breadth or height. So example for this one is very thin surface coatings. Then two dimensions. It has only length and breadth. For example, nano wires and nano tubes. Three dimensions. It has all parameters of length, breadth and height. Example is nano. So we all have a doubt of being how small this nanoparticles will be. So if you have this doubt, you can imagine it is approximately 40,000 times smaller than the width of an average human hair. So this 1 nanometers is only 3 to 5 atoms wide. So the size of some of the examples of substances having nanometer size is the size of a hydrogen atom is 0.04 nanometer. The size of protein is approximately 1 to 20 nanometer. Future computer chips may be manufactured with the size of 180 nanometer. Diameter of a human hair is approximately 10 micrometers. At nanoscale, the physical, chemical and biological properties of materials differ in fundamental and valuable ways from the properties of individual atoms and molecules or bulk matter. So these are some of the examples of nanomaterials. So see the carbon nanotubes. The carbon nanotubes are given in the second picture and the first one is the DNA structure. See the size of the DNA structure is 50 nanometer shown here. So, based on the size and shape of the nanomaterials, they can be classified into so many things like nanoparticles, nanocapsules, nanofibers, nanowires, fullerenes, nanotubes, nanosprings, nanobelts, quantum dots, and nanofluids. Then we'll see what are the properties of nanomaterials. So, nanoscale effects on properties. Catalytic property. So, better catalytic efficiency through higher surface to volume ratio. So, nanomaterials possess better catalytic efficiency. Then electrical properties. Electrical conductivity will be increased in ceramics and magnetic nanocomposites. This increased electrical resistance in metals. Magnetic properties. So, increased magnetic conductivity up to critical grain size, super paramagnetic behavior will be obtained. So, mechanical properties. So, this nanoscale materials will have improved hardness and toughness in metals and alloys. So, the ductility and superplasticity of ceramic particles is also increased. Then, optical properties. Spectral shift of optical absorption and fluorescence properties is observed, and also there is an increased quantum efficiency of semiconductor crystals. Spherical. So, increased selectivity, hollow spheres for specific drug transportation and controlled release can be possible due to this nanoscale effects. This is applied mostly in the drug delivery. Biological properties. The permeability of this nanoscale properties is increased through biological barriers, that is membranes, blood-brain barrier. So this improved biocompatibility. Regarding the changes in color, normally small particles absorb color, leading to some colors changes. This is a size dependent property. So color is a size dependent property. So see, gold which can be readily formed into a nanoparticle gives a number of color changes due to this nano converting property. Gold colloids have been used to color glasses since early days of glass making. Ruby glass contains finely dispersed gold colloids. Silver and copper also will give attract colors when they are converted into nanoparticles. Application of nanoparticles. Nanoparticles have wider application in various fields. We'll see some of their applications. Nanotechnology applications in medicine. Because of their small size, nanoscale devices can readily interact with biomolecules on both the surface of cells and inside of the cells. So these property can be used in so many areas of the body that they have potential to detect and deliver the treatment. Nanoparticles can deliver drugs directly to diseased cells in your body. Nanomedicine is the medical use of molecular sized particles to deliver drugs, heat, light, or other substances to specific cells in the human body. Quantum dot. These will identify the location of cancer cells in the body. And nanoparticles, they deliver chemotherapy drugs, that is the drugs to treat cancer cells to minimize the damage to the healthy cell. Nanoshells, they concentrate the heat from infrared light to destroy cancer cells with minimal damage to surrounding healthy cells. Nanotubes, they are used in broken bones to provide a structure for new bone material to grow. Nanoshells as cancer therapy. These nanoshells are injected into the cancer area and they recognize the cancer cells. Then by applying the near infrared light, heat energy is produced by the light absorbing nanoshells that kills the tumor cells while leaving the neighboring cells intact. See, this is how nano shells kill the tumor cells selectively. First, the nanoshells detect the cancerous cell, and then the infrared light is passed over that cell, which destroys only the cancer cells. So nanoparticles are used for molecular imaging purpose for detection of malignant lesions. So for this purpose, ferric oxide nanoparticles are used. Nanowires can be used as medical sensors. Nano-sized sensing wires are laid down across a microfluidic channel. As the particles flow through the microfluidic channel, the nanowire sensor pick up the molecular identification of these particles and can immediately relay this information through a connection of electrode to the outside world. These nano devices are man-made constructs made with carbon silicon nanowire. They can detect the presence of altered genes associated with cancer and may help researchers pinpoint the exact location of these changes. We can see this nano sensor working through this video. See, first the particles are passed through the microfluidic channel. So here nanowires are used as sensors. So this nanowires detect the biomarkers of cancer. So next one is nano computing technology. So in the past, shared computers are used. Thousands of peoples are used for a mainframe of computer. Now presently we are using personal computers, but in future ubiquitous computing will be possible because thousands of computers sharing each will be shared by each one of us. So computers will be embedded in walls, chairs, clothing, lights, switches, etc. So this is possible only because of this nano computing technology. So nano materials can also be used in sunscreens and cosmetics. Nano-sized titanium dioxide and zinc oxide are currently used in some sunscreens as they absorb and reflect UV radiations. Nano-sized iron oxide is present in some lipsticks as a pigment. They can also be used as fuel cells. So these nano-engineered membranes can be used in catalytic processes which could enable higher efficiency in fuel cells. Displays. Nanomaterials can be used as displays. So nanocrystalline zinc selenide, zinc sulfide, cadmium sulfide and lead telluride are candidates for the next generation of light emitting phosphorus. Carbon nanotubes are being investigated for low voltage field emission displays because of their strength, sharpness, conductivity and inertness, which may make them potentially very efficient and long lasting emitters. They can be used in batteries. With the growth in portable electronic equipments, that is mobile phones, navigation devices, laptop computers, remote sensors, there is a great demand for lightweight, high energy density batteries. Nanocrystalline materials are candidates for separator plates in which batteries, because of their foam like, that is aerogel structure, which can hold considerably more energy than conventional one. So, nickel metal hydride batteries made of nanocrystalline nickel and metal hydrides are envisioned to record less frequent recharging and to last longer because of their large grain boundary area. Catalyst. They can be used as catalyst in many chemical reactions because of their high surface area, and hence they provide high catalytic activity. There are some magnetic nanomaterials which found many applications. So magnets made of nanocrystalline yttrium, samarium, cobalt grain possess unusual magnetic properties due to their large grain interface area. This could lead to applications in motors, analytical instruments like magnetic resonance imaging used widely in mostly hospitals and microsensors. Nanoscale fabricated magnetic materials also have applications in data storage. Devices such as computer hard disks storage capacity is increased with magnetic nanomaterials. Medical implantation. Nanomaterials can be used in medical implantation also. In some cases, biomedical metal alloys may wear out within the lifetime of the patient, but nanomaterials increases the lifetime of the implant materials. Nanocrystalline zirconium oxide is hard, wear resistance, biocorrosion resistance, and biocompatible. So that this can be used as an alternative material for implants. Nanocrystalline silicon carbide is an candidate material for artificial heart valves, primarily because of its low weight, high strength, and inertness. Water purification can also be done by this nanomaterials. This nano engineer materials can be used in the water purification processes, particularly in desalination process. These nanomaterials can also be used in military battle suits. So enhanced nanomaterials form the base of state of art, that is battle suit, that is being developed. So they can be used to incorporate sensor to detect or respond to chemical and biological weapons. So like this, there are so many applications are there for nanomaterials. The future is full of the future will be full, which will be full of this nanomaterials. The future will become a nano world by the application of this nanomaterials. Thank you.